Welcome to SanfordFlipMath. This is Algebra 2. We are working through the Springboard book. We are working through a unit on rational expressions, rational equations, rational functions. And rational, just to remind you, just has to do with the idea of ratio. So a rational function is a function that would be like y equals or f of x equals, and it's the ratio of two polynomials, or it's a function that can be written as the ratio of two polynomials. It doesn't have to be polynomials. It doesn't have to be written in that form initially, but something like y equals 1 over x, y equals x plus 2 over x minus 3. Even something like y equals or f of x equals 3 plus 1 over x would be considered a rational function, because that could be written as 3x plus 1 over x if you get a common denominator and combine them. So those are some possible examples of functions that would be considered rational. What happens with this, and while I'm here, this would be considered the parent function for rationals. It is the cleanest, simplest version of a rational function, of a function that has the features that are typical to what are called rational functions. In fact, I'm going to take a quick look at the graph of this. So y equals 1 over x. And if I go, so I'm going to go to the y equals menu. And there are a couple of ways, depending on which calculator you have, there are a couple of ways you can type this in. I need to warn you that you need to be really careful about grouping. So for this equation, just the parent function, y equals 1 over x, it's not terribly difficult. You can type it like that. Another way to type this would be, if you have a fairly up-to-date TI-84, if you push the alpha key, that creates the top row of keys become what are considered soft keys. In other words, they take on different functions. So like if I push y equals, so alpha and then y equals, notice this first choice says n/d, so numerator / denominator. It's a way to make a fraction actually look like a fraction. So I could type in y equals 1 over x that way also. The only real difference with this is in the table, and sorry, this is a little sidebar. In the table, what happens is when you do the fraction notation, you get fractions. Isn't that clever? Is it going to wake up? There it is. Okay. Whereas if you type it the other way, the standard just division bar kind of thing, it ends up looking like decimals. So just kind of be mindful of that. If you don't care, then, well, gee, you don't care. I like the fraction one because it looks like fractions, but all right, so the point of this is we want to take a look at the graph. So let's go to the graph. Okay, so here comes the blue one, here comes the red one. They're both the same thing, 1 over x or 1 over x. This is kind of a bizarre looking graph. Some things to consider also is your calculator can't keep going closer to the x-axis. If you notice this thing, look, it should keep going like this forever, and it just can't. That's all. So there are limitations to that. The calculator has issues with pixel width, and every pixel gets an x value, and so it can only get so close. It's not a perfect tool. Also worth noting that it keeps going forever to the left and to the right. Now, what's really kind of interesting, though, remember the equation we're looking at here is y equals 1 over x. And if we start thinking about x and y values, like if I put in 0, what's 1 over 0? What's 1 divided by 0? Exactly. So that was my Dora moment, sorry. It's undefined. I can't graph it. So notice there is no y-intercept. There's nothing on the y-axis. And you can get closer and closer and closer to the y-axis. Like if I use the x value 1, 1 divided by 1 is 1. If I use the x value 0.5, 1 divided by 0.5, 1 divided by 1/2 is actually 2. If I use the x value 0.25, that's 1/4. 1 divided by 1/4 is really 4. It's reciprocal. If I do 0.1, 1 divided by 1/10 is 10. If I do 0.01, 1 divided by 1/100th is 100. All right, so the idea is as I get closer and closer and closer to the x-axis, these y values start getting ginormous. That's a math term, ginormous. Huge, huge. So the y values get bigger and bigger and bigger. And so what ends up happening is this graph gets closer and closer to the y-axis, but never actually touches it. Okay, so quick little note to self. That line is, in this case, is called an asymptote. An asymptote, it's not a bad word, an asymptote, careful how you abbreviate that, is a line, the graph gets closer and closer to without actually reaching it. So it gets closer and closer to the y-axis, but it's not actually going to touch it. Okay, hit pause if you need to keep writing that if you're writing down all the details. Okay. All right, well, you might be thinking, well, hey, there's another asymptote. So, for this graph, the y-axis is an asymptote. Okay, so x equals 0, also known as the y-axis, is a verticals up and down, asymptote. 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 Well, if you notice, doesn't it? What's going on here as we get closer and closer, or as we go farther and farther to the right? So, for instance, if I push trace, okay, and where do we go? Oh, look, you can't see the trace button. So I'm actually on the 1 over x line. If I go, oh, there it is. See, it wasn't showing up because it wasn't there. It was on x equals 0. So watch what happens as I go farther and farther to the right. Okay, let's hear. No, it won't do that. All right, sorry. Okay, so I have to keep tap, 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 tap. It's kind of annoying. Okay, so notice what's going on with the y values. What's going on with the y values? They're getting smaller and smaller and smaller. So the question is, now in order to actually touch the x-axis, the y value has to be 0. So when is it actually going to touch? When is it actually going to get to 0? I mean, I see it getting smaller and smaller and smaller. When does it actually get to 0? Well, let's play with this a little bit algebraically. Hang on, we're going to let it catch up because I don't know if it'll let me write and keep moving at the same time I was clicking like crazy. Sorry, the time is clicking. It's really important that you have a solid understanding about what's going on here. All right, well, I'm going to let that play for a minute. I'll come back to it. Okay, so if I have this equation, y equals 1 over x, and if I want to know when does y equal 0, so I'm going to put 0 in for y, and I'm going to solve it for x. Well, how do you solve this for x? Well, I'm going to multiply both sides by the denominator to get rid of the denominator, and x times 0 is 0, so 0 equals 1. 0 equals 1. Remember, I was looking for the x value that makes y equal 0. Well, 0 doesn't equal 1, I'm sorry to tell you. So if I tried to put 0 in here, I know that doesn't work. 1 divided by 0 is undefined. If I put 1 in here for x, 1 divided by 1 is 1. That's not 0. So it appears to me y never equals 0. Okay, so for this specific graph, for this specific function, not only is x equals 0, the y-axis, a vertical asymptote, but y equals 0, also known as the x-axis, is a horizontal asymptote. Okay, so horizontal going side to side like the horizon, think about it as you're looking out to the sea. Okay, so that's what an asymptote is. Okay, an asymptote basically, for a vertical asymptote anyway, is what's considered a discontinuity. A continuous graph is a graph that is connected. You can draw the whole thing without picking up your pencil, without picking up your pen, without picking up your marker. That's what a continuous graph is. That's what a continuous function is. So a discontinuity is a break in the graph. It's a spot where you can't draw and connect it to the other side. So like the graph we just drew, this is a very, very rough sketch. But as I'm drawing along, I I have to stop, pick up my pen, my pencil, my marker, and then go back up to the top and kind of keep on going. So right at x equals 0, there is a discontinuity. Well, there are a number of types of discontinuity, and we're not going to spend a lot of time worrying about that right now. But one of the types, we're going to talk about two types right now. One of the types of discontinuity would be a vertical asymptote. That is a discontinuity. We don't consider horizontal asymptotes discontinuity. They're just a feature of what's going on with the y values as we keep putting x values in. There is one other kind of discontinuity that we're going to see in what we're doing right now, and that's called a removable discontinuity or a point discontinuity. And let me give you an example of a function that would do that. Let's say I had something like 2x plus 2 over x plus 1. Okay, 2x plus 2 over x plus 1. I'm going to just come over here. Let me clear my stuff off. Okay, and I'm going to clear both of these out, and then I will type in the other function. Okay, so let me again make a big stink out of this. So it's 2x plus 2 over x plus 1. So one way to type this in would be parentheses 2x plus 2, close parentheses. Oh, I missed the plus, sorry. Plus 2, there we go, divided by x plus 1. If you have an older TI-84 or maybe a TI-83 or maybe a TI-82, 81, you have to type it in this way. Okay. If you have a newer TI-84 or another graphing calculator that will actually type things in as fractions, you can type it in like this. Again, that was alpha y equals. And so it's 2x plus 2. You can use the down arrow to go to the denominator, x plus 1. And it just looks a little more like normal. Excuse me. Okay, so just a quick little note. If you just type it in like this, what this means is 2x plus 2 over x plus 1. The division would happen here, and that creates that fraction, but the 2x and the plus 1 would not be part of that fraction. So this is a big deal. Okay, you need to really watch for this, because I see people make this mistake all the time. It's happening less and less now that more people have the fraction button or whatever available. Okay, but you just need to be aware of that. All right, so again, these two functions should be identical. I should see the same graph for both of them. And oh, my window's funky. That's it. Notice you see the blue line go across and then the red line. All right, I'm going to zoom 6. This is zoom standard. This is kind of like the go-to screen. And there it is. Now, what's weird about this is it looks like a horizontal line. Some people call it a straight line. I think every line is straight. But doesn't this look just like, it crosses at y equals 2, doesn't this just look like y equals 2? So that y equals 2 isn't terribly exciting. Now remember, the equation that we were working on was this one. Now, so the question is, how in the world could that have shown up as y equals 2? And the hope is that you're seeing, after we've spent all this time simplifying rational expressions, that there's a common factor there that divides out. Okay, so that's really the same thing as y equals 2. Okay, now there's a bit of a but coming. I'm going to go to the table, and I want to show you something that is kind of sneaky that you probably didn't see. Okay, so let me scroll. Ooh, look at that. What is that, and why is it there? So it says error at x equals -1. Well, the hope is you're remembering, that's funny, about some of the things we've done as we've simplified. And tell me what's going on with that. I mean, isn't x equals -1 a restricted value? x equals -1 would make this denominator 0. So what that means is at -1, at the x value -1, there isn't supposed to be a point there. Now, because of the window that we have set up here, it's not obvious what's going on. If I push trace, the calculator, as I mentioned, is not a perfect tool. So if I try and go to x equals -1, it actually misses that point because the pixels aren't falling exactly on x values that are nice. Okay, so I'm going to do something sneaky. I'm going to go to what's called zoom decimal. So I'm going to the zoom button, and I'm going to do decimal. And what this does is it lets my zoom points be a little more specific, a little more nice. Notice what just happened? Do you see the point that's not there? I know it's funny to try and say, do you see the point that's not there? Can you see something that's not there? By definition, you can't. Sorry, think about it. All right, so what's going on now? If I push trace, I'm cruising along, y equals 2, y equals 2, y equals 2, when x equals -0.7, -0.8, -0.9, negative point. Oh, look, it's gone. And look at the y value they're showing. Okay, so if I go a smidge to the left, oh, that would be to the right. If I go a smidge to the left, a smidge to the right, I have that y value, but it's not there if I'm at -1 because -1 is a restricted value. Okay, so a point discontinuity happens when there's a restricted value, but it's not one of the asymptotes. Okay, so what just happened is those divided out. And so x equals -1, though, is still a restricted value. So we still need to list all of the restricted values. Oh, sorry, that says equals. I'm saying not. Okay, so just so we're clear, what we would say is there's a hole or a removable discontinuity or a point discontinuity at x equals -1. The domain, though, would be x not equal to -1. So -1 is the location of the hole. What's allowed in my function? Not -1. All right. Well, I know we're already getting close to 20 minutes. I'm gonna let's do maybe we already talked a lot about this. Well, I think we need to, so we're just gonna go ahead and keep rolling. All right. So vertical asymptotes happen when the denominator equals 0, but it's not something that divides out. So like for instance, in this case, I can't reduce out to x. So x equals 0 is going to be a vertical asymptote. Not only that, the domain will be x not equal to 0 because it's a restricted value. Okay. Vertical asymptotes, domain, and if there are any holes, this graph doesn't have a hole, those will all be very closely related, very connected. They're not interchangeable, they're not always identical, but they're very, very similar. They're very, very close. Okay. Horizontal asymptotes are a little more tricky to find, but let me also throw the vertical asymptote on the graph. So what we do is we represent this by a dotted vertical line. Okay. To get a little graph going here, I'm going to just put in a few points. And so we already know 0 gets us undefined. If I do 1 over 1, it's 1. If I do 1 over 2, it's 1/2 or 0.5. So if I do, again, just a couple of points. Okay, so here's 1, 1, here's 1, 2, 1/2. If I put in, I'm just going to put one fraction in. 1 over 1/2 is back to 2, so this is what this side is starting to look like. Okay, now we've talked about the fact that it's not going to get to 0. We saw that graph. That y equals 0 is going to be a horizontal asymptote. Y is not going to ever get to 0, so that's going to be the range. Okay, there aren't any holes on this graph. Okay, we'll talk a little bit about the details on how. All of the negatives of these points are also on this graph. So something like this. And again, don't hit the x-axis, don't hit the y-axis. Okay? This is the parent function. This is how everything starts out. Okay, now as we put in other details on the equation, there's some weirdness that's going to happen. So we have to know how to track that. Okay, so here we go. Let's do another one. Okay, so there's some more stuff going on here. Some things to note. First of all, let's talk about restricted values. Because the denominator can't equal 0, x can't equal 3. Well, shockingly enough, that's going to be the domain. If it comes from a factor that does not divide out, it's also going to be the vertical asymptote. So the vertical asymptote is x equals 3. So I'm just going to go over here to x equals 3, and I'm going to put in a dotted line. Okay, we're going to use that as a guideline for our graph. The hard thing about this is going to be, how do you know the horizontal asymptote? Well, one way to do this is to type it into the calculator and just trace on the graph. I'm going to show you a way to be a little more sneaky. As x gets huge, as x gets bigger and bigger, the +1 and the -3 play less and less of a role as x gets bigger because it becomes much more about the terms with x in it. So what we're going to do is locate the highest exponent of x, that term, and we're going to match those terms up. So in this case, it's just 2x and x. So we're going to match up 2x and x. So the horizontal asymptote is going to be y equals 2x over x. In other words, the x's divide out 2. It's not that the +1 and the -3 don't matter in the graph. They do. But what takes a bigger role is the horizontal asymptote. And actually, that horizontal asymptote becomes the end behavior. We aren't going to make a big deal about end behavior here. But notice the line I just drew was that y equals 2 line. You'll be shocked to know that the range is probably y not equal to 2. Okay, and then we could put in some x values and find some y values, but honestly, at this point, I'm just going to do a little sketching, and it's going to look something like this. I actually just kind of peeked at the y-intercept by putting in x equals 0, so that would be -1/3 is the y-intercept, and that's how I located that point. And you can type in the calculator and see what the rest of this graph looks like. Okay, I'm getting freaked out about time, so. Okay, I'd like to do one more that involves a hole also, so a point discontinuity, and I want one that has both. Yeah, there we go. This is a better example. Okay, so here we go. I'm going to factor because it's much easier to see what the restricted values are and what's going on if we can factor. Okay, so look at that, x plus 1, x plus 1. Now you need to be careful because, yeah, all that's left is x plus 2, but note that x plus 2 is on the bottom. But there has to be something on the top to kind of keep this thing a fraction and that on the bottom, so we have to put a 1 there. Okay, so some things to write down. Vertical asymptotes come from the factors that don't cancel out in the bottom. It's only the bottom, it's not the top. So, I'm sorry, the vertical asymptote is x equals -2. Because x can't be -2. So this is the line that it never touches. So the domain will have an x not equal to -2 in it. But remember that there was a restricted value from that x equals -1 also. So but because it canceled out, it's a point discontinuity. But it's also in the domain, or a value restricted from the domain. Okay. Now let's do something about horizontal asymptotes. Now I just said to match up the highest exponent of x in the numerator and denominator. Now here's the problem. There isn't an x squared. We're still going to match it up. There's an x squared in the bottom, but not in the top. We're still going to match it up, and we're going to cheat. We're going to throw an extra little x squared in there, and so that's what's going to match up. So this horizontal asymptote is going to be 0x² over 1x², which hey, x squared goes, but 0 divided by 1 is 0. So you are correct in assuming that the range will not include 0. Now there will be another value here. Okay, that's something that we're going to have to go hunting for. And I will tell you that it happens as a result of this x value. All right, so let's do some graphing based on what we have. Okay, I already know there is a vertical asymptote at x equals -2. I know there's a horizontal asymptote at y equals 0, which is the x-axis. Okay. If I use the y-intercept, which is kind of a sneaky way to get a point to get started, the y-intercept is going to be 0, 1/2. You don't have to use that point. Half. You don't have to use that point. Good one, Sanford. But I like to use that point because it's easy to get. So that's going to be there. And usually these end up being in opposite little quadrant-y kind of things. Technically it's not quadrants because they're not axes, but it's like that. So it's going to look like this. And the other part will be down here somewhere. Okay, now if weirdness happens with exponents, they don't always have to be across from each other like that, but you can type it into your calculator and see, confirm it. Okay, so one other thing to point out, remember that x is not supposed to be equal to -1. So somewhere over here, what we're going to do is draw a little hole to represent this point is missing. Okay, so notice what's going on there. So that hole is at -1, at x equals -1. The problem is, the other little box that we drew here, that point has a y value also. So this is at -1. Oh dang, how do we get the y value that goes with it? Okay, so here comes the sneaky thing. We can actually substitute -1. We just can't do it in the original function. If we take this -1 and put it right here though, it won't make the denominator 0. So if I do 1 over -1 plus 2, that's 1 divided by 1. Well, don't do that. But 1 divided by 1 is 1. Okay, so the other value not allowed in the range, not possible in the range, was y equals 1. All right, in the interest of going long just for long's sake, okay, that's not true. I don't like to do that. Okay, so I'm gonna go and we're gonna try and summarize some of this. Okay, so vertical asymptotes come from the denominator can't equal 0. So anything that makes the denominator 0 is a vertical asymptote unless it cancels out. Okay. Point discontinuities happen from the denominator equaling 0 again, but something that does cancel. Horizontal asymptotes we find by matching the highest exponent, that was funny, of x and then reducing. Okay, and again, remember that the domain is closely related to the vertical asymptotes and the point discontinuity, so x can't be anything that makes the denominator equal to 0. And the range generally comes from the horizontal asymptotes and the y value of any hole. In other words, point discontinuity. All right, so that's my quick recap of everything. All right, so I know this went long, and I'm sorry we had to cover a lot of ground. This is all a brand new thing. Remember, if you want to come back and just look at examples, for the future, you're certainly welcome to do that. And I guess we need to be done. Thanks, SanfordFlipMath. We're out. Bye.